As the second application of the Biot-Savart law, I'm going to solve this problem. In here we have a circular circuit, a ring which carries a current I, and the radius of the ring is given as the capital R, and we would like to compute the magnetic field at the center. Later we are going to see that we can also compute the magnetic field anywhere on the symmetry axis of that ring, but that's a slightly different problem than this one. So this is kind of simpler, so therefore I'm just going to solve this separately. So this is the top view, all right? So what we do is, again, the first thing that we should do is to choose the coordinates, but fortunately in here we don't really get a real integration, so as a result I can solve this problem without introducing any variables. So as a result I'm just going to take a length element in here, so that's dl. This is a vector, right? The direction, along this direction the current is I. So I take a segment in here. So with this segment, of course, the radial position is like that, right? The position of the point with respect to the segment is given by this. So therefore, the radial unit vector is directed towards the center, which means the angle between dl and r is 90 degrees, right? So as a result, if I pass to writing down the Biot-Savart law for this element, I'm going to first write down the vector expression. So it is dl cross with the r unit vector divided by r squared. All right, so once we write down this expression, we usually do two things. We compute its magnitude, we compute its direction, right? Let's start with the direction. So the direction is basically out of the page, out of the screen. So dB is a vector which is pointing towards us. So that's the simplest thing. Actually, when you consider any point within that plane, any point within the circle is going to have a magnetic field vector for any segment which is pointing out of the board, right? So for any point outside, of course, the magnetic field, the net magnetic field will be pointing into the board, but that's something else. But at least for all the points inside this ring, you can safely say that this magnetic field is always pointing perpendicular to that plane, and it's always pointing towards us, right? Let me erase this and then concentrate again on the magnetic field at the center. So that's the direction. Once we know the direction, then that's basically easy to integrate, because in that case we just need to consider the component of the magnetic field along that direction only, and that's it. So as a result, I'm going to continue with this expression. So therefore, I need to write down the components. So let me just write down the, let me take the z direction as the direction which is pointing out of the board. So therefore, this is going to be the z component of the magnetic field, right? So what I'm writing down is not really the magnitude, but it's the component. So therefore, this is equal to dl multiplied with 1 multiplied with the sine of 90 degrees and divided by r squared, right? That's the expression. Sine of 90 degrees is 1. 1 is 1. So as a result, we get this expression, mu 0 I divided by 4 pi dl divided by r squared. Normally, r squared, r would be a variable, but in that case, wherever I choose my segment on the ring, it doesn't matter. I'm always going to get the same distance to my point in question. So as a result, this capital R in here is essentially a constant, right? So that means when I integrate this, so BZ is the sum of all of these Z components. So by this integral, I mean I need to divide the circle into many segments. For each segment, I compute this dB and then sum over them, right? So therefore, we have a symbolic integration like that. Since I haven't chosen any variables of integration, this is still symbolic, but we know what it really means. In any case, I know that this mu 0 I over 4 pi is a constant, capital R is a constant, so therefore I can take them out of the integral. And so therefore, I have within an integral, it's just the integral of dl. So at this point, I just interpret this symbolically again. So this is actually a recipe that tells me to divide this ring into small pieces, right? Compute the length of each piece, length as a scalar, compute the length of each piece, and then add them up, right? First divide, find the length, and add them up. This is basically circumference, right? I just need to realize this geometrical fact in here. So once I understand this, I don't need to use any variable. But if you're not comfortable with this, just go ahead and use some kind of a variable, like an angle variable in here. That can be done, but in any case, this integral is 2 pi r. So therefore, let me write it in a separate place, or in here, at the center in here. So therefore, B is equal to mu 0 I divided by 2r. So that's the answer to that question. So the magnetic field at the center is pointing towards us, and it has a magnitude given by this. So since I have time, let me also say something about the direction. So this is the three-dimensional view. So let me first draw this picture of the ring. Right? It's not a good picture. So to give the impression of this three-dimensionality, I then try to draw the axes in here. So let's say that this is the center. Z-axis is like that. And x-axis would be something like that. It would be entering like that and then going out from this part of the wire. So that's the x-axis. Y-axis would be like that, so it will enter inside the wire and then go out, right? So perhaps at this level you can understand something about the three-dimensionality in here. So therefore the magnetic field at the center in here, sorry about that, let me also show the direction of the current in here and then show the direction of the magnetic field. So only in that case the magnetic field at the center is pointing along the positive z direction. Okay, so as a result, I was going to say something about the direction, so let me try to complete this. So we usually use our right hands to find the directions. So let's remember how we have used the right hands before. So one way is this. So I'm going to draw the picture in here of my right hand, and I'm going to choose a different color in here. So you can imagine that you hold the wire like that with your four fingers. You just squeeze the wire with your right hand, with your four fingers. So as a result, your hand is going to look like that. It's a very strange hand, but whatever, just accept this as a hand. So your thumb shows the direction of the current, and the other four fingers show the direction of the magnetic field at the place they are placed. So as a result, if you are holding your hand in like that, in that case, these things basically show the direction of the magnetic field right above this wire. So therefore, it indicates a magnetic field like that. But if you want, you can just rotate your hand too. So in that case, of course, you can also find a magnetic field in here too. So you can easily see that this is also pointing outward, right? So that's one way. I have said that you can also use this three-finger rule of the cross product. That was the first method that I have mentioned. There's still a third method of finding the direction in here. So for this reason, I'm going to erase this hand in here. I'm going to draw a different hand. This time, though, the role of the magnetic field and the current has been switched. So I'm going to use a yellow color for this one. So in that case, what you do is you just orient your thumb along the direction of the magnetic field, or in the direction that you guess the magnetic field to be, right? And in that case, your other four fingers would be like that, right? Let me show the direction of the magnetic field. So if your thumb shows the magnetic field produced by that circuit at the origin, right, at the midpoint of that circle, in that case, the other four fingers show the direction of the current. So as a result, to use this last rule, you have to orient your four fingers along the direction of the current and then see which direction your thumb shows. That's basically the direction of the magnetic field at the center. Okay, let's just keep this in mind. And so as a result, by using either of these rules, you can easily see that the magnetic field lines in here basically are things like that, curves like that. They are not circular, of course, but they are curves that somehow cross this disk defined by that ring from inside, and they cross it along the positive z direction, right? They cross it like that along this direction, and then they go around. So at some point, of course, they are oriented along the negative z direction. So outside that disk region, they cross the plane along the negative z direction, and they go around, and then somehow they get connected to where you have started from, right? So as a result, you can draw the magnetic field lines like that, right? So they just go around like that. So you can draw all of them. There's a very special line in here that passes from the center. So this is is parallel to the z-axis at all times. So this is a line that starts from minus infinity of the z-coordinate and goes to plus infinity of the z-coordinate.